Let's talk about finding the volume of a solid by using a slicing method. So the graph above shows the base of an object. Compute the exact value of the volume of the object given that cross sections perpendicular to the base are equiangular, or if you like, equilateral triangles. Okay, how to begin? Well, I like to visualize things, and so I'm going to take a look at the three-dimensional representation of the shape first, just to get an idea of what I'm doing. We have as its base a trapezoid, and on top of that trapezoid, I am stacking equilateral, or if you like, equiangular triangles. And so that means, what is an equilateral or equiangular triangle? And an equilateral or equiangular triangle is a triangle where all the sides are the same length, or all the angles are the same length. In an equiangular triangle, the angles all have a measurement of 60 degrees. The sides, however, can change lengths depending if it's a bigger or smaller base. But the one thing is, all of the bases are the same. So let's take a specific equilateral triangle and let's stack it on top of our trapezoidal base. So I'm just going to say this is my trapezoidal base, right? This is what I'm going to sit on top of. And let's stack on top of that an equilateral triangle. So here we go. I'm going to put one on top. And when I make it, I want to make all my sides about the same length, right? So now I'm going to put another one. Not a really excellent detailed drawer, but what we should be picturing as we're doing this is we're creating equilateral or equiangular triangles that all have the same distance across the bottom as the sides. Now, as I get towards this part, the pointier part of my trapezoid, right, my triangles are going to get smaller. That's because the bases, respectively, are getting smaller. So these equilateral triangles will be getting shorter. So I don't know if you can picture this, probably do a way better drawing than I did, but we're creating now a three-dimensional shape. Now, how do we use calculus to get the volume? Well, really, we're going to use integration. We're going to sum up the areas of all of these equilateral triangles across from start to finish, across the entire interval of which this blue base is spanning. So to add up all the areas for each of these equilateral triangles, I first need to know what the area is for a single equilateral triangle. So what is the area for a single equilateral or equiangular triangle? The area is, if you recall, square root 3 over 4 times the length of the base squared. That's important because what are we doing again? We're going to add up the areas, we're going to add up the areas of each of these equilateral triangles all the way across. There are infinitely many of them, so we're going to take an infinite sum of these areas. All right, so let's set up those integrals. What are they going to look like? Now, I said integrals. That's because I'm looking ahead. If you look at this problem, right, let's see. Where are these triangles sitting? Well, the base runs from here to here, right? So this would be the base of one of my equilateral triangles. Here's another base. And what do you observe about these bases? Well, the distance for those bases, or the lengths of those bases, is determined specifically by the functions here that are outlining my trapezoid. And I observe that right here in this area, I have a top function. Here I have a different top function. And so that's telling me I'm going to need a couple different integrals to set up my problem. Let me be more specific. I'm going to first integrate my triangle portion right here, because the lengths of each of these triangles are determined by this distance here that runs along this top, green top, and this green bottom. Then I'm going to integrate or look at all the rest of the equilateral triangles because those bases run along this function, the blue function here. So let's set up our integral. We start with our limits. We're going to begin for the green portion going from 0 to 1. So we're going to integrate from 0 to 1 the areas of the triangles that fall in that green region. So I'm going to denote that by putting green here. So that's the square root 3 over 4 times the base squared for all the equilateral triangles that have this as their base here. And then I'm going to add to it the other equilateral triangles, and they are running from 1 to 3. And I'm going to put those in blue because they are the bases there are determined by the top and bottom functions, which are my blue functions. Now, I'm not sure if I'm making sense, but we're going to put this all together here. So these triangles here, these equilateral triangles here in the green region, okay, have bases, and those bases are determined by this green function here and this green function here. Specifically, what is this green function? Well, it's a line, and if we like, we could think of it as the form y equal mx plus b. Specifically, this line has a b or y-intercept of 0 and a slope of rise 2, run 1. In other words, that equation right there, this line is actually the line y equal 2x. In a similar fashion, I could find the bottom line. There's a lot of symmetry going on, and that line is y equal negative 2x. And if you recall, the way to get the distance between two graphs or two functions is we take top function minus bottom function. And so this distance here along the bottom is simply going to be the top function, 2x, minus the bottom function, negative 2x. And so the length of the base for the equilateral triangles in the green region is simply 4x. That becomes the base for the equilateral triangles in my green region. These are my green region triangles. So let's put that into that integral. We have from 0 to 1, the square root 3 over 4 times 4x squared. 4x again represents that base, that distance from the top green to the bottom green function, which represents, correspondingly on our picture over here, the distance over here for the base along these equilateral triangles. Let's continue and let's look at the blue base for those equilateral triangles sitting on the blue base. The distance goes from here to here. What is the top function? Well, this is the line y equals 2, and this is the line y equals negative 2. And so if I want to take a look at those two functions, y equal 2 and y equal negative 2, and I want to know what is the base or the distance here to here, I could think of it as the base is 2 minus negative 2, which is 4. Or I could simply count, right? 1, 2, 3, 4 units is how long those bases are along the blue region. So putting that information in our integral gives us that we are integrating from 1 to 3, the square root 3 over 4 times 4 squared dx. And 4, if you like, is that distance here for the blue base for those equilateral triangles that are sitting along the blue part. That's those equilateral triangles. So if I add up the areas of all of these equilateral triangles, in other words, if I sum or integrate all of those regions, I get the volume for the entire shape, specifically the volume for this three-dimensional solid. So let's integrate. First rule, I like to pull out my constants, so I'm pulling out a square root 3 over 4, but I can also pull out that 4 squared, so I'm also going to take out a 16. So really, all I have to integrate is x squared dx. Same thing over here. I can pull out all my constants. I'm pulling out square root 3 over 4. Again, I'm pulling out a 16 and from 1 to 3 of just dx. We integrate, so doing a little cancellation here in the front. Gives me that the 4 cancels with the 16. The 4 cancels with the 16. I think this is the easy part, and you'll be all set from here. The hard part, I think, is the setup. But we have 4 times the square root of 3. Antiderivative of x squared is going to be 1/3 x to the 3rd power from 0 to 1. 4 square root of 3, antiderivative of dx is just x from 1 to 3. And continuing my integration, what do I have? So I have 4 square root 3 over 3 times 1 cubed minus 0 cubed plus 4 square root 3 times 3 minus 1. And doing the math gives us that the volume for this shape then is going to be 4 square root 3 over 3 plus, this is 1, this was also 1, 4 square root 3. I could stop there if I want. That's cubic units for the volume. Or if I like to get a common denominator, I would rationalize, well, I don't rationalize, excuse me. If I get a common denominator, that would give me 4 square roots of 3 over 3, 12 square root 3 over 3, or if I like 16 square roots of 3 over 3. That is the volume for the solid resulting by putting equilateral triangles on this original trapezoidal base.